With most of the formalism groundwork now laid, let's go on to the next section, which has to deal with a lot of fun things, in particular the Dirac notation, which I think most people struggle with until they just grapple with it a few times. I think the best way to do this is to show how it's used in a problem like this. And in this problem, we wish to show that the projection operators are idempotent, meaning that we get the same result after applying it multiple times as we do applying it once. And in this case, we wish to apply the operator twice, hence p hat squared equals p hat. And if you're are unfamiliar with the projection operator, it's defined as such, where p hat is equal to what we call the ket vector, defined as such, and the bra vector, defined as such, for any normalized vectors in V. Again, part of being in the Hilbert space. And so from here, what we wish to do is determine the eigenvalues of p hat and characterize its eigenvectors. Okay, so we have to be a little careful with some of the notation as well. The equal sign here simply means that, we get the same result when applying it to a vector. It's not that the two things are actually equivalent. So just be aware of that. And also note that the bra vector here is actually a linear function of vectors. We're trying to get something out of it, so whenever I have a bra and a ket, we get just a number out, so it's operating on the ket vector. And then similarly, when I take an operator and I smack it into a ket, I get another vector out. So it lets you know that operators are matrices in this linear algebra sense. So let's be careful with that moving forward and see how we can prove this statement. So to start off with, we need to remember that operators need to operate on something. And in this case, we wish to operate on the beta vector that we define here. Just like in the commutators, we operated on a test function. Similar process here, we're operating on a test vector. Same idea. Let's also recall real quick that the square here just simply means we're applying the operator twice. So that's what we do here and color coding it. When we apply the projection operator in blue onto beta one time, we see we get what's in the curl brackets. I'd like to now point your attention to what this is actually representative of. Here, if we recall, the ket vector from the last part that's just equal to a column vector with n entries in one column. So we say that its dimension is n by 1. Okay? So if I have a ket vector and I have what we call with the inner product definition, I have the bra vector has to be a row vector. Okay, we saw that in the definitions. It's just one row with several columns. And of course, with dimensionalities, that means that we have 1 by n, because we have n many columns for however many entries, of course, in a finite sense. And with that being said, since these are the definitions for the finite space, which is what we're going to have in the physics scape for quantum mechanics, not really dealing with the infinitesimal or infinite vector spaces right now. But what we can say is that the inner product is defined just like we would with the integrals, except now in the finite sense, is just the dot product, right? We've seen that in the finite sense with vectors before, no big deal. But whenever we do matrix multiplication, i.e. dot products, we note that the matrices have to have the inner dimensions matching. And what we see here is that in this product, we have the bra multiplying by the ket vector. So the inside dimensions have to match, i.e. n and n. And then the outside dimensions are the result. So the outside of the bra is 1, the outside of the ket is 1, so we get a 1 by 1. And that lets us know that we are actually a scalar product here. And as a scalar, we know we can move scalars through the operators with linearity with no big problem. And that's why we are able to bring this out front here. Of course, if we have an inner product, we also have an outer product. And that's what we see here. And so this returns back now that the dimensions are switched, we have the ones matching, and the n's are the outer dimensions in the multiplication, so, or the product, and so we're left with an n by n. Okay, so think about something like a cross product, for example. That takes the, we get another vector out of it. And in this case, again, since we're the same vector, we get an n by n. No big deal there. Moving forward, though, we just have to be careful of this dimensionality, especially when we deal with other states or other systems. So just be aware that that's what's going on here. So here, now that we're done with that little mini lesson, this here in the red bracket is just a scalar. So again, move it out front of the projection operator because it doesn't give anything to us. So you see, now that we have the projection operator acting on the ket vector alpha, again, apply the same definition. And here you see that we get the outer product of alpha alpha in the green. And again, that outer product just simply means we're looking at what is the projection of one vector onto another in the vector direction. That's what it's showing us. Okay, so, and even in multivariable calculus, you see this projection vector happening. But also let's recall that this is not only a scalar here with the blue and red, or blue and green, but it's equal to 1. And this is due to the fact that we were normalized vectors. So with that, we can go ahead and just get rid of it, since any multiplication by 1 in this case gives us the same thing back. And that's how we end up with this statement here. That's a pretty fun, walkthrough of applications, but I think it's important to see all the nitty-gritty details here so you can see how the dimensions of these products start to play out, especially moving forward when we have to deal with matrices. So be aware, it's definitely going to get a little more hectic, and let's see how we can use this statement with the first statement and conclude what we need to conclude. Alright, so clearly then, we saw what applying the operator twice on beta did. That gave us alpha, beta, alpha. But of course, we got that same result when we had it just operated on once, because alpha, beta was a scalar and we moved it through. So we were able to show that here, applying the operator twice just gave us another scalar, but the scalar was a factor of 1 because of the normalization. So we're good. We're done. It doesn't matter anymore. That being said now, since we operated on it a test vector beta, we can cancel them out, so it would hold for any vector beta. And so we see that we conclude exactly what we were aiming to conclude. And, again, pretty fun example. These have some interesting characteristics, though. And again, go back to the physical intuition of what projection meant. In the eigenequation, the eigenvalue equation, we read that the operator, again, we're assuming that this is an outer product operator because we know that a matrix multiplied by a vector gives us out a vector. So that's what we mean by outer product. We have the dimension matching and all that other fun stuff. Linear algebra is going to help you in all of the rest of the chapter because of this. But nonetheless, the eigenvalue states that applying an operator, which is just a matrix, onto a vector gives us some scalar multiple of the vector if the vector that we're applying it on is an eigenvector. Okay, so that's why we call this an eigenequation, eigenvalue equation. The history can be read up on. It's pretty cool though, very useful. And of course, we could have the trivial case of the eigenvector being 0, but that's not of interest. We're looking for the non-trivial vector, so we don't want gamma equals 0. And if that's the case, what we can tell you is that lambda is an eigenvalue since we know that this doesn't equal 0. And so applying this operator twice, again, using the same color code, we have the blue act on gamma here yields the right-hand side of the equation. So that's why we have a blue gamma or blue lambda and blue gamma, although this doesn't really matter. This eigenvalue lambda is a vector is a scalar, so push it out front and reapply, and you see we get the same result. So actually we get a lambda squared, a lambda squared. In this case, I'm going to leave the colors alone because of what we will see next. Wonderful, wonderful. Having had previously shown that the operator was idempotent, meaning that no matter how many times we apply it, we get the same value, we could use this fact, and since it holds for any vector, that would include the eigenvectors. So we apply it, we see on the left-hand side we get the double eigenvalues. On the right-hand side we only get the one eigenvalue. So here we see that we have an equation where we have the double eigenvalue minus the single equals 0. Cool. Don't cancel them because you're going to miss a whole set of solutions doing that. Solve an algebraic equation with 0 in it. As you see, factoring out the green leaves us with a lambda minus 1, and so we see we have two eigenvalues, which should make sense in the case of the fact that we applied this operator twice. So these kind of self-checks are definitely helping. So we have a lambda equals 0 and a lambda equal 1. Okay, you're kind of seeing the writing on the wall for what's to come here. And so what we can do is the eigenvalues are best characterized, or we need to characterize the eigenvectors by their eigenvalues. And to me, organizing that is best in a chart. And so for the case of 0 here, we see that the eigenvalue equation turns into a 0, and this is good for any vector orthogonal to alpha. And I think it's worth taking a look at to y. And so here in case 1, on the top right, we see that the eigenvalue equation descends down into this, where we have the projection operator, which gives us the matrix again, just a nice and more compact way of writing it. That is equal to the 0, so we get the 0 on the right-hand side acting on whatever vector gamma is. And so here what we can say is that, again, since we want the non-trivial vectors, we don't want alpha, the ket vector, or ket vector of alpha equal to 0, so we get rid of all of them. This is the statement of the inner product and the ket vector equals 0 only holds if the inner product is 0. And what this tells us exclusively is that we know if the inner product is 0, that alpha and gamma have to be orthogonal. So the eigenvector can be anything that is orthogonal to the alpha that is creating the projection operator. So that's a pretty cool result and pretty intuitive to me. If I take the projection operator of the x direction onto the z direction, of course I'm going to be 0 because those two things are orthogonal. That's what this is trying to tell us. Moving on, though, what we see for case 2 is going to be a little more tedious if you're not careful. So here we see that in case 2 for lambda equal 1, descend down the eigenequation, as you see here. What we see is that we have some multiple of the vector, because of this inner product leads to a scalar, equals the vector of interest, the ket, and then it equals the eigenvector here. This only is true if the eigenvector is a scalar multiple of the vector of interest in alpha. So what we say is that this holds for all A in the complex world. It can be anything, and we say that that's okay because eventually it will cancel, insofar as such that we define the gamma vector, the ket vector, to equal some multiple, again scalar, of alpha. And if so, we plug this into this equation here, and we see that we can descend down with linearity and inner products and prove it. So A, being the yellow, is a scalar to both of these. Push them out, factor them out. And then here we see that we have the inner product to A with itself. Again, since we're normalized, that goes to 1. And so we end up with A with the alpha ket vector is equal to A alpha ket, or alpha ket, whatever. So either way, we get equivalent statements here because the constants will cancel. And so it doesn't matter what kind of constant it is, and we see that we can factor it out to the linearity, so we're good for any multiple that is a complex number, so long as it is a scalar number, and that could be of the new axis that we're looking at or the new basis. So that's pretty cool. A lot of ranting here, but I think it's important to show how we can get to these things and use our intuition. It's going to be a lot to deal with, so this is how we can work through these type of questions. And definitely, the eigenvector, eigenvalues will come back in full swing. So if you're not used to those, please get used to this equation and how to find eigenvectors, because you have to use the eigenvalues to find the eigenvectors. It might be even worth doing a video on that. But nonetheless, take care of all the dimensions since we're dealing with vectors and matrices, and then we could develop the toolkit for that later. But as far as this question, I think we did good proving everything we needed to, so I'll see you on the next one. And with that, thank you for watching. Until next time, stay curious and happy learning.